Hello and welcome to a project on data augmentation, specifically in the realm of high quality MRI imaging from Sarah, Dominic, and Colin. There are three main moving parts to this project. A variational autoencoder used to generate new data samples from existing ones, a generative adversarial network used to create realistic images from said data samples, and a diffusion model used to further refine the images that are generated by the generative adversarial network. The result of this is a high quantity of high quality synthetic MRI brain scans. Now, what is the point of these synthetic images? Well, there's a lot of ethical and practical concerns when it comes to the sourcing of MRI images for machine learning research in the first place. Actual authentic MRI scans are, first of all, regulated by HIPAA and other privacy regulations and must be ethically sourced, um, which is often not very easy, especially because, as with a lot of anatomical information, especially the anatomical scans, there's often identifying patient information just baked into the image itself, not to mention the demographical data attached to it. Additionally to that, there are the issue of just the accuracy of the image, the quality of the image. Um, the accuracy and the quality of two different MRI machines might not be the same, not to mention the way they're set up makes the image look different, uh, how they're directly angled, and the way the patient was sitting, and the specific type of machine itself, the specific brand and model of machine. Not to mention the difficulty in ensuring that a neurologist or radiologist has actually come across and accurately annotated these images. Um, and so, how do you deal with all these varying practical and ethical concerns of authentic MRI images? Well, you create synthetic ones. These synthetic MRI images are very useful when it comes to machine learning because they can be generated in much higher quantities than any actual authentic MRI scans are going to be able to be found. And you can ensure that they are accurately annotated, that they are high quality, and that they've all been harmonized to ensure that any biases from the specific actual hardware machine that took the images has been removed, and that the model's not going to be confused by that. And this can all be done while retaining important anatomical qualities for disease research and machine learning in training. In the regards of related works to our project, well, there are um, quite a few examples actually, but the three main ones right here are immunity, medical image synthesis, and brain imaging generation. Immunity doesn't specifically generate new images, but it did show the use of harmonization between multiple different sites in training data. It found that by in removing the differences in how the images looked that were taken from two separate machines, so they looked like they were taken from the same machine, the model was able to enhance its accuracy and not get as confused by the differences in the hardware that was used to take them. And in the medical image synthesis paper, it was found that using data augmentation and anonymization is in fact helpful for the training of models, improving their accuracy while also having synthetic images that are not tied to an individual despite preserving the actual features necessary to detect these diseases, which is just more ethical for patient privacy. And while the brain imaging generation paper found pretty much similar when it comes to the enhancement of training, it found that using a diffusion model resulted in a probabilistic distribution of brain images, ensuring that there was accurate representation of different age and gender and volumes of different kinds of brain matter within the resulting images. What is the proposed method of this paper? Well, we want to combine the strengths of a variational autoencoder and generative adversarial network with the strengths of a diffusion. We use the variational autoencoder to generate new data images that are refined into realistic images by the generative adversarial network. These images will be anonymized from all patient identifying information while also retaining the important features necessary. And then we want to pass these through a diffusion model to ensure that fine details and important anatomical features are not lost in the process or lost to the random noise.
So our first goal was to create a VAE which would give us a solid and continuous latent space that we could pull from to generate new images. So we used an encoder and a decoder with 3 convolutional layers, which I found was the optimal depth after we tested a few different configurations. And to train the autoencoder, we used a mixture of reconstruction loss and KL divergence to measure overall loss. The reconstruction loss is exactly what it sounds like, so how faithful the reconstructions are to the original images. And the KL divergence measures the distance between probability distributions. So in a VAE, it's used to ensure that there's a continuous latent space that we can pull new images from. I used a variable beta to control the balance between these two, which I tuned using Optuna, which is a hyperparameter tuning software. And basically, it comes up with points within a range that it's given and continuously optimizes the parameters to those points. We also use it to decide on the best dimensions of the latent space, the best optimizer, and the best learning rate. So here you can see some visuals from the tuning process. In the beginning, we had a very high ratio for reconstruction loss and a very low ratio for KL divergence. So that's beta at 0.1. And you can see that it all starts to kind of converge to the same image. With a beta at 0.5, we have medium kind of grainy output. And with a beta of 2.0, the reconstructions actually look really, really good, but that's because the reconstruction loss ratio was very high. However, the rest of the latent space samples looked something like this. So as you can see, we're getting bad results because of the imbalance in the ratios. So these are some visuals from the tuning process. And as we continue to balance these, we obtained results that looked more like this. So these are the best losses that we had, around 0.07, with an image resolution of 256 by 256 pixels. So after that, I added attention layers and skip connections, which improved the quality a little bit, but still not exactly what we were looking for. And it's definitely hard to distinguish the different structures in the MRI. So that's where the GAN comes in. In the GAN, we decided to use it to improve image quality. The GAN is composed of a generator and a discriminator. So the generator creates fake images from random noise, and the discriminator tries to tell whether those images are real or not. This is an example of adversarial training where the generator and the discriminator compete against each other, and the generator continuously tries to fool the discriminator by generating increasingly more realistic images. So in our current architecture, the GAN is pulling a vector out of the latent space, decoding it, handing it to the discriminator, which is checking it against the input images to see if it can distinguish between them, and then returns a probability back to the latent space to continue to optimize it. Once the latent space is optimized, the images get passed to the decoder so it can generate the new data set. And the GAN optimizes using a combination of adversarial and VAE loss. So the VAE is going to give us a continuous interpretable latent space, and the GAN is used generally to overcome the issue of blurriness that we saw in the last inputs. So again, we used hyperparameter tuning to increase the image quality. One of the main issues we ran into here was mode collapse. So the generator learns to tend toward the same output each time. Basically, this means that it found the simplest possible solution to this problem, which would continuously fool the discriminator, but not create the representation of the data that we're looking for. So as you can see, the results are pretty uniform and again, kind of converging to the same result. I tried a couple of techniques to improve this, which you can see on the right, such as WGAN or Wasserstein GAN, which uses a different type of distance to measure loss, providing a smoother loss landscape. I also added gradient penalty, which penalizes the gradient if it produces overly similar results and forces it to have some more diversity, as well as several techniques during training, like batch normalization and noise injection, where you disturb the inputs during the training to force the generator to create more varied outputs. This took us from the first image to the second, but did not lead to the level of improvement we were looking for, which is where the diffusion model comes in.
We also wanted to add elements of diffusion models to our overall model because of their ability to progressively denoise the data. The core idea is essentially inspired by forward and backward processes. In the forward, the data is gradually corrupted by adding Gaussian noise in multiple time steps until it becomes pure noise. And at this point, a model will then learn to reverse this noise in order to recover the data purely from the noise. These models are very powerful for generating high quality, diverse samples, and actually have recently in isolated comparisons have outperformed GANs in tasks such as image generation because of their stability and ability to preserve very small details. We use a U-Net architecture model to predict the noise at each time step in the forward diffusion process. The process simulates corruption, and the backwards refines the image, like I said, from the latent space. The model was trained on real images. The loss function was compare the predicted noise with the actual noise added in order to calculate the grading updates. And the VAE-GAN decoder would generate an initial image, and then it would be able to find the entire process. Through reverse diffusion, the model refined the image, which improved both its detail and quality, which we actually saw greatly improve the model in comparison to strictly VAE-GAN architecture. We believe this is because of the attention that it placed on the very small details of the images instead of simply the overall pictures to them. There's also generated more impressive brain scans as well as better ones, which we think will be able to really show in the medical field and will be a great help for them. And it also worked very well combined with the VAE-GAN architecture. This is definitely important because we wanted to layer these few concepts together. We thought we wanted to combine as many as we can. Not as many as we can, but the best we can. And in doing so, we think we generated a very good pipeline for brain scans. And because, going off of that, in the real world, this is a very important field. There's a lot of people out there who need their brain scanned in order to find diseases like Alzheimer's or dementia. And in this sense, we want as many AI models to eventually be able to identify these diseases. And in doing so, the first step is to get enough training data for those models, which is essentially the little pocket of the world that we found our project to fit in under. As far as future goes, we think that adding a few different aspects or changing it slightly, we wanted to tweak it. One thing we were looking at was the learning rate. If we could maybe have a little bit closer range on that, as well as the number of alphas. But those are very, very small changes that we think could really excel this going forward. We do believe that VAE-GAN and diffusion model, the synthesis of these three, greatly improved image generation quality over large-scale data sets, specifically within generation of brain mapping. We believe that this is a very cool and exciting step to be going, and we are looking forward to learn more about it. But we do think that this should be used more often in the field, specifically for generating data to train AI models.